Okay, this is number 15 on page 473. Let's have your attention up here, please. Austin. It's hard to hear on the video if you're talking, okay? Especially when you're close to the camera. So you need to have it be quiet. You can answer my questions, of course, but otherwise just try to pay attention up here. I'm going to try to review lots of stuff with this one problem. Number 15, it's off lesson 9-2, page 473. In the study cited in exercise 11, researchers collected data shown here on a self-esteem questionnaire. At alpha equal 0.05, can it be concluded that there is a difference in the self-esteem scores of the two groups? Okay? And the data that's given, they give you leavers and stayers. If you look back at number 11, you can see what the whole story is on this problem. But we're just going to look at the data here. X bar sub 1. So the first sample mean is 3.05. These are grade point averages, actually, of science majors, I believe. X bar sub 2 is 2.96. So the second sample mean, the average grade point of the stayers is 2.96. The first standard deviation of the sample is 0.75. S sub 1, 0.75. And the second standard deviation, S sub 2, is also 0.75. The first sample size was 103. So there's 103 people, 103 leavers, and 225 stayers. Okay, it says, can it be concluded that there is a difference? So to me that sounds like the claim is that there is a difference. So that the means of the two populations would not be equal. Okay? So then the null would be that they are equal. You will always use a Greek letter up here in the null and the alternative hypothesis because Greek letters stand for population measurements, parameters. Okay, in this case it's population means. And normally we don't have information about the entire population, so we're trying to make a prediction or a claim about the population means. We know the sample means, so it wouldn't really make sense to talk about the sample means up here. We already know what's going on with the sample means. We're trying to predict what's going to happen with the population means. Okay, step B. Now it depends which method you're using. Okay, does it tell you to use the p-value method, doesn't it?
Yeah.
Okay, so I'm going to use the p-value method on this one. But off to the side, I'm going to show you what you do if you're doing the traditional method, so you can see both methods. Okay. For traditional methods, step A would be the same. Same either method. Step B, if you're doing the p-value method, you find the test value. So you go to this method. Z equals, you x bar sub 2 minus x bar sub 1. Does that look right on the formula sheet? Or is it 1 minus 2? It could be done either way, but what's it say in your formula sheet? 1 minus 2. Okay. Like I said, you can do it either way as long as you subtract the x bars, but let's go x bar sub 1 minus x bar sub 2. So that's 3.05 minus 2.96 minus, over here you have mu sub 1 minus mu sub 2. Well, in the null, we're saying they're equal. So we're saying they could be equal up here. So when you subtract them, what would you get? On the bottom, you have the square root of standard deviation 1 squared over n, is that right? Okay. So 0.75 squared divided by 103 plus standard deviation 2, 0.75 again squared divided by n sub 2, 225. This is our test value. Let me ask you this. What if the sample means were exactly the same? What if these two numbers were exactly the same grade point? What would this answer come out to then? 0. Because you get 0 divided by something, 0 divided by anything will give you 0. So if the standard deviations are, if the sample means are the same, you're going to get 0. And when you get a z-score of 0, that means you're in the middle of the distribution, which means you would not reject the null. Okay? And wouldn't it make sense if the sample means are the same? We'd probably assume that if the sample means came out exactly the same, that we would probably say that the population means are probably also equal. Okay? If there's a big difference between these numbers, okay? if there's a big difference between these numbers, we're going to get a z-score that's not very close to 0. We might get something bigger than 3 or smaller than -3. That would tell me that we're out in the tail. Then we would reject the null. We would reject that they're equal. Okay? Now step B over here would be to find the critical values. So let's do that. You don't have to write this on your papers, but I want to just make sure you understand that the difference here. Critical values, what's it say alpha is? 0.05. Alpha equals 0.05. So if you look at our distribution here, it's 1 or 2 tailed? 2 tailed. So you take half of alpha, so alpha divided by 2 would be 0.025 in each tail. And subtract 0.025 from 0.5 to get 0.475. Then you look in your z-chart for 0.4750. Does anybody know what z-score that gives me?
1.01.
Say that again. Look up 0.4750. It should be one that's fairly common that you've heard before. 1.96. Okay. So what we have here, if you were doing it the traditional method, which you're not, but I'm just showing you how. I want to show you the difference between the two methods. If you were, it's 2-tailed, so it'd be plus or minus 1.96. And the area outside of the critical values is called the alpha value. And that's your probability that the null is true, that you will still reject the claim, or reject. If the null is true, that you will still reject it. So there's a 5% chance here that even if the null is true, that we'll end up rejecting it, which would be an error, called a type 1 error. Okay, anyway, what does, let me finish this off. Anyone type this in or know what that comes up to? 1.01. Okay, so that's our test value. Okay. Step C, what you do is you look at your z-distribution, your standard normal distribution. If you're doing the p-value method, you go 1.01, which 0 is always in the middle, remember? So we're 1.01 standard errors to the right of the mean. This value right here is called the p-value. But actually, you're going to have to double it because there's going to be, it's 2-tailed, so you got to count both sides. So go to your z-chart. This time, look up 1.01. So go to 1.0 on the left side, go to 0.01 on the top. What number does that give you right there?
0.3438.
3438. Okay. If we subtract that from 0.5, so we're going to take 0.5 minus 0.3438. That's going to give me 0.1562, I think. Is that right? I think I did that right. Okay. Then that's the area to each tail, so then we double that. We'll times that by 2. 0.3124, does that look right? That's our p-value. Okay. What that means is that if the null is true, there's about a 31% chance that we will still get a z-score of 1.01 or a more extreme value. In other words, 1.24% chance we'll get a test value of 1.01 or one that's further out in the tail. Now, if we were doing the traditional method, now we would do the z-score. We go through that whole process, this whole thing right here again, and we get z equals 1.01, which falls in, right in there. Here's 0 right here. So 1.01 would maybe be about right there. So then, if we're in the white region, we say reject or do not reject. Yes, C is the test value. Yeah. I'll recap here in a minute. Do not reject the null, which is the same thing you'd say over here. Because if your p-value is greater than alpha, you'd say do not reject the null. So step D is going to be the same in both of them. Do not reject null. Here you say do not reject because your p-value is bigger than alpha. Here you say do not reject because your test value is in the white non-rejection region. And then let's step E, which will be the same on both of them again. If you're not rejecting the null, what should you say about the claim? Let's see. If we're not rejecting the null, that means we think the null is true, which means we think this is false down here, the alternative. So what would we say about the claim? Right. There's not enough evidence to support the claim. Okay? I'm not going to write it all out. That's what you'd say. There's not enough evidence to support the claim that the population mean, or the mean of all levers and stayers, or the mean grade point average of levers and stayers are not equal. There's not enough evidence to support that claim. Okay, so here's a recap. When you do p-value method, step A is the same for traditional and p-value. You write out your null and your alternative. When you're doing the p-value method, you figure your test value in part B. Then you figure the area outside of that test value for part C. And that's called your p-value, or probability value. When you're doing the traditional method, you don't do the test value until you get to part C. Parts B and C here are the same, but different methods. But you have to do the critical values then. So in the traditional method, you have to find the critical values, but you don't have to find the p-value. Okay? And again, the area outside of the critical values, this is called alpha. It's the probability of type 1 error. The area outside the test value, 1.01, and negative 1.01, that's called the p-value. So alpha and p-values are both areas. Okay? Anyone have any questions about that? It's a lot of information, but that's what we're trying to get to understand. All right, I don't think we'll do confidence